Dear students, in this class we will try to understand what is known as D. Broglie's hypothesis, or in other words, it is also known as wave particle dualism. So we will try to understand what is D. Broglie hypothesis and, or in other words, what is known as wave particle dualism. So before trying to understand D. Broglie hypothesis, let me remind you what we discussed in the previous class, that is about Compton scattering. So what is Compton scattering? Compton scattering is an experiment in which an incident X-ray beam collides with the target material, that is an incident X-ray is colliding with an electron. In the meantime, the incident X-ray beam undergoes scattering, and we observe that in the scattered X-ray beam there will be two wavelengths, one wavelength as that of the same wavelength of the incident one, and the other wavelength lambda dash, which is found to be always more than that of the incident one. So in order to account for why there is an increase in the wavelength, in order to account for this enhancement of the wavelength, the Compton was able to explain the so-called Compton shift by considering the X-rays as what? By considering the X-rays as made up of n number of photons, each photon carrying the energy E equals to h nu. So the Compton was able to explain the Compton scattering or the enhancement in the wavelength by or the Compton shift by considering an incident X-ray beam as made up of what? N number of photons or the particles, and it was assumed that there is going to be a one-to-one collision between the incident photon and that of the electron, and in this collision there is going to be a loss of energy. The photon is going to lose the energy, and that loss of energy is coming out as what is known as a scattered photon having less energy or having more wavelength. In other words, in this case, we are clearly considering an X-ray beam as made up of n number of photons, or the particle nature is assigned to that of the light, that is an X-ray beam. But at the same time, we know that X-rays are basically the electromagnetic waves. So X-rays are treated as electromagnetic waves, but to explain the Compton scattering, we are considering them as the particles, that is the photons. Means what? Now the X-rays is behaving a dual nature. X-ray is behaving like a wave. We know it's electromagnetic wave, but to explain the Compton scattering, we are considering the X-ray as made up of n number of photons, or we are assigning the particle nature to the X-ray. We also know that X-rays undergo diffraction, that is in the Bragg's diffraction experiment, the so-called Bragg's law, we know that the X-ray beams undergo diffraction. What is diffraction? Diffraction is basically a wave phenomenon. The phenomena like interference, diffraction, polarization, they are all the phenomena which are assigned to the wave nature of light. So we know that as per the Bragg's diffraction, X-rays undergo diffraction. Means what? Here in case of Compton scattering experiment, we are considering X-ray as made up of particles, and we know that X-rays are basically electromagnetic waves, and in the Bragg's diffraction experiment, we know that X-rays are undergoing the so-called diffraction phenomena, which is purely a wave nature. Again, if you take the example of a photoelectric effect, the photoelectric effect explained by the scientist Einstein. So what is photoelectric effect? Photoelectric effect is basically an effect in which an incident photon or an incident light having suitable frequency, when it falls on a metal surface, what happens? There is going to be liberation of electrons from the metal surface. The liberated electrons, we call them as what are known as photoelectrons. So this phenomena, the phenomena in which an incident light having suitable frequency is made to fall on a metal surface, when it falls on the metal surface, there will be liberation of electrons from the metal surface. Those liberated electrons, we call them as what are known as photoelectrons, and the phenomena is what is known as photoelectric effect. So again, in this case, Einstein explained the photoelectric phenomena by considering the incident light as made up of what are called as photons. Each photon carrying the energy E equals to h nu. So Einstein says that the incident light is now assumed to be made up of n number of particles, like which he calls them as photons. each photon is carrying energy E equals to h nu, where h is the Planck's constant and nu is the frequency associated with it. So the incident light was assumed to be made up of n number of photons. When that incident light falls on the metal surface, there is going to be an one-to-one collision between the incident photons and the electrons. During this collision, what happens? The photon transfer all its energy to the electron. The photon transfer all its energy to the electron. As a result, the electron gets more energy and they are liberated from the metal surface. So what it means? The entire photoelectric effect is explained by considering light as what? Light as made up of n number of particles. What it calls them as what are known as photons. So it is a collision between an incident photon and that of an electron. During this collision, the photon transfers all its energy to the electron. As a result, the electron gets more energy, so it is totally removed from the metal surface, which we call them as what are known as photoelectrons, and the phenomena we call it what is known as photoelectric effect. Means what? Photoelectric effect is explained by considering light as made up of a number of particles, which we call them as photons. And again, the Compton effect was explained by considering the incident X-ray beams as made up of what are known as photons. Means Compton scattering experiment and the photoelectric effect are the two clear examples to say that light is behaving like a particle. Otherwise, you cannot explain neither the Compton scattering phenomena nor you can explain the photoelectric phenomena by considering light as a wave. So we can explain both these phenomena only if we consider light as made up of particles. So light is behaving like a particle. On the other hand, we have the standard phenomena of physical optics, which are those: the interference phenomena, the diffraction phenomena, the polarization phenomena. What are these? All these phenomena, the interference or the diffraction or the polarization, we always consider light as a wave. Light is a wave. So only by considering light as a wave, we explain interference, diffraction, polarization, and so on. But we have the experiments like Compton scattering and the Fourier effect, in which we are considering light as a particle. So this clearly indicates that light is exhibiting dual nature. Light is exhibiting dual nature. Sometimes light is behaving like a particle, sometimes light is behaving like a wave. What are the examples for wave nature? Interference, polarization, diffraction. What are the examples for particle nature? The Compton scattering experiment and the photoelectric effect. So now it is very clear that light is exhibiting the dual nature. Sometimes it behaves like a particle, sometimes it behaves like a wave. So by observing all these phenomena, the scientist known as Louis de Broglie of France, the scientist known as Louis de Broglie, he came to a conclusion. He understood all these concepts and he gave a hypothesis. What is known as the de Broglie's hypothesis? So what is de Broglie's hypothesis? De Broglie says that since nature loves symmetry, if light behaves like a particle in some circumstances, if light behaves like a wave under some other circumstances, then the entities which normally behaves as particles will also exhibit the properties clearly attributable to the waves, and he calls those waves as what are known as matter waves. What is that? De Broglie says that since nature loves symmetry, if the light behaves like a particle in some circumstances, if it behaves like a wave in some other circumstances, then it is possible that the entities which normally behave like particles will also exhibit the properties of waves under some other circumstances. And he further says that a particle in motion is always associated with a wave. What is that? If you have a particle like an electron or a proton or a neutron, a particle in motion is always associated with a wave. That is, this particle in motion is always having a wave associated with it. So this wave, he calls them as what are known as matter wave. So what are these called? They are called as matter waves. So what are matter waves? Matter waves are the waves associated with a moving particle. So these waves, we call them as the matter waves, and he also gives the wavelength of these waves. The wavelength of the matter waves is given by lambda equals to h by p, or in other words, lambda equals to h divided by m into v. So what is lambda? Lambda is the wavelength associated with a moving particle. What is h? H is the Planck's constant. What is p? P is the momentum. What is momentum? M into v, mass into velocity. What is m here? M is the mass of the particle, like electron, proton or neutron, which is in motion. And then what is v? V is the velocity with which the particle is moving. So he says that a particle in motion is always associated with a wave. That wave, he calls them as what is known as a matter wave, and the wavelength of these waves is given by an equation lambda equals to h by p, that is equal to h divided by m into v, where m is mass of the particle, this may be electron or proton or neutron and so on and so, and v is the velocity with which this particle is moving. And this wavelength is what is known as the Broglie's wavelength. This wavelength is what is known as B. Broglie's wavelength, that is lambda. Right? One thing you make it very clear that matter waves are entirely different waves. They are not like electromagnetic waves. So from this equation, if you observe here, lambda equals to h by p, and lambda equals to h divided by m into v. So the wavelength of the B. Broglie wave or a matter wave depends upon what parameter? Depends upon one parameter, that is the velocity v with which the particle is moving, because h is a constant, m is a constant. So more the velocity with which the particle is moving, lesser the B. Broglie wavelength. Lesser the velocity with which the particle is moving, the B. Broglie wavelength is going to be more. So what is lambda here? In this case, so this is going to be lambda. The distance will be to trough, or the distance will be to crust. So this wavelength, we call it as what is known as B. Broglie's wavelength. So sometimes we call these waves as what are known as matter waves. Sometimes they are also known as B. Broglie waves. Sometimes they are also known as what are called pilot waves. They are also known as pilot waves. But one thing is very important. What is that? Matter waves are entirely a different kinds of waves. They are not the electromagnetic waves. So in general, we can say matter waves are the waves associated with a moving particle like electron, proton or neutron, and the wavelength of these waves is given by lambda equals to h by p, that is equals to h divided by m into v, where m is the mass of the particle and v is the velocity with which the particle is moving. So what is that we came to know from this de Broglie hypothesis? From this de Broglie hypothesis, we came to know that the particles which we know that electron or proton or a neutron, which are basically having particle nature, they will also exhibit the so-called wave nature. They will also exhibit the so-called wave nature. Or in other words, any particle in motion is always having a wave property. In other words, there is what is known as a wave-particle dualism. What is wave-particle dualism? A particle is behaving like a wave, and a wave behaving like a particle. Particle behaving like a wave. What is an example? Particle behaving like a wave. What is the first example? That are the de Broglie hypothesis. What is the example for a wave behaving like a particle? The experiment like complex scattering experiment. The experiment like photoelectric effect, because in those experiments we have explained those phenomena by considering light as made up of particle. So it is very clear that there is what is a wave particle dualism. Means particle is sometimes behave like a wave will sometimes behave like a particle. Based upon these things, the de Broglie was able to give his hypothesis, what is known as a de Broglie's hypothesis. Based upon that, he defined what are called the matter waves, or the pilot waves, or the de Broglie waves, and he was able to give an expression for those waves by the equation lambda equals h by p or h by m into v. So this de Broglie wavelength can also be explained or can also be expressed in some other forms. Which are those forms? We can say lambda equals to h by p, one form, that is equals to h by m into v, the other form of a de Broglie wavelength, or we can say lambda equals to h by the square root of 2m e. This is one more form of a de Broglie wavelength. What is the m? Again, mass of the electron. What is the e? The energy associated with the moving electron. This is one more form of a de Broglie wavelength. We can also express this as lambda equals to h divided by square root of 2mev. Square root of 2mev. Why? Because this energy can be explained or can be expressed as E into V. So what is m? Mass of the electron. What is E? Charge of the electron. And what is V? V is the applied potential difference, that is the voltage. V is the applied potential difference or the voltage. So the de Broglie wavelength can also be explained as lambda equals to h divided by root of 2mev. If you look at this equation, here h is a constant, Planck's constant, having a standard value, and mass of the electron again a constant, having the standard value. What is E? Charge of the electron, again having the standard value. Is h, m, e all are constant. All are constant. So if we substitute all these values, and if we calculate them, we get a standard value. What is known as lambda equals to 1.266 into 10 raised to minus 9 divided by root v. Or in other words, we can say lambda equals to 1.266 nanometer divided by root v. So how do you get this? By substituting the value of h, the Planck's constant, 6.63 to 10 raised to minus 34, m, mass of the electron, right, that is 9.1 into 10 raised to minus 31 kg, e, charge of the electron, 1.6 into 10 raised to minus 19 coulomb. By substituting all these values, if we simplify, what we get is, we get the answer as 1.266 divided by root v. So this is again the one more form of the de Broglie wavelength. So what is V? V is the applied potential difference. So now we can observe from this equation, by applying a different voltage, we can produce de Broglie waves of different wavelength. More the applied voltage, lesser the de Broglie wavelength. Lesser the applied voltage, more the de Broglie wavelength. So we can produce de Broglie waves, which are basically the waves associated with a moving particle by applying different voltages to these particles. Means if you have an electron, if you want to accelerate this, what you have to do? You apply certain voltage. Once you apply certain voltage, this electron will be accelerated. So more the applied voltage, lesser the de Broglie wavelength. Lesser the applied voltage, more the de Broglie wavelength. Or in other words, we can produce de Broglie waves or the matter waves or the pilot waves of different wavelength by applying a suitable potential difference or a suitable voltage. So this is all about the de Broglie hypothesis or what is known as wave particle dualism. So I will brief. In this class we have understood what is the de Broglie hypothesis, what are matter waves, the waves associated with the wave particle, and what is the wavelength of these waves. It is nothing but lambda equals to h by p, known as the de Broglie wavelength, or h divided by m into v. M is mass of the particle and v is the velocity with which the particle is moving. And we also know that these waves are known as pilot waves or sometimes as de Broglie waves. and these are the different forms of de Broglie equation. H to the root of 2me in terms of energy and lambda. This is again one form of de Broglie wavelength in terms of voltage and charge of the electron and the mass, and this is again one more form of the de Broglie wavelength. And finally, we come to know that the particles like electrons, protons, or the neutrons, they also exhibit the so-called wave nature. It's very common that we are familiar with the wave nature, that is the diffraction, interference, and the polarization, the wave nature of light. And from quantum scattering experiment and photographic experiment, we understood the particle nature also. But this is entirely a different thing, that is particles exhibiting the wave nature and having a corresponding wavelength. So that phenomena was explained for the first time by a scientist known as de Broglie, what is known as de Broglie's hypothesis. I think we'll stop at this point in this class, and in the next class we will try to verify the de Broglie hypothesis by an experiment, what is known as Dualism German experiment. Till then, you take care. Goodbye. Bye bye.